Good morning, my dear students. As you all know that we had completed with the first lesson of the current, electricity, Ohm's law and resistance. Now we shall start with the second lesson of the current, electricity. The second lesson is DC circuit and measurement. In this lesson we will study about the electric cell, formation of a battery, that is the combination of cell in a series combination and parallel combination. Then we will also study about Kirchhoff's law, which is very important because you certainly get one numerical over Kirchhoff's law. Then meter bridge, that is the practical part of the lesson, and also potentiometer. So it is a very important chapter. Okay, so please we'll begin with DC circuit and measurement. When in a closed circuit containing an electric source like a cell or battery and a resistance or capacitor through which current flows is known as circuit. In this, the electrical energy is transformed from one place to another. We are going to study about cell, electromotive force, circuit containing cells and resistances, and measuring devices. So we all know that in a circuit we require an electric cell. So the first question is, what is an electric cell? An electric cell is a source of electrical energy which maintains a continuous flow of charge in a circuit. It consists of two rods of different metals which are called electrodes or plates. These are immersed in a liquid called electrolyte. This liquid has property that on immersing the plate in it, one plate becomes positively charged, the other one becomes negatively charged. When the two plates are connected by a wire, the charge begins to flow, which maintains the supply of charge to the plates. A chemical reaction takes place. Thus, a cell converts chemical energy into electrical energy. So, a cell is a source of energy. A cell is a source of electrical energy. The first point that we have to discuss in a cell is electromotive force in a cell. The work done by the cell in forcing unit positive charge to flow in the whole circuit is called electromotive force. Or in simple words we can say it is the potential difference across the cell in an open circuit. Or when no current is being drawn in the circuit, the potential difference across the terminal of the cell when no current is being drawn from the cell. Clear? So electromotive force is nothing but potential difference, that is between the terminal of the cell when no current is being drawn from the cell. So the potential difference in an open circuit is known as electromotive force. Its SI unit is volt. Then the next one is potential difference or terminal voltage. What we call it is the terminal voltage. The terminal voltage is the potential difference across the terminal of the cell when the current flows through the internal circuit, that is through the external circuit of the cell. That is, we can also define terminal voltage as the potential difference across the terminal of the cell when the current is flowing in the circuit. Okay. So terminal voltage is the potential difference across the end of the circuit when the current is flowing in the external circuit. If we have to define electromotive force in terms of work done, then electromotive force in terms of work done is the work done by a cell in forcing the positive charge to flow in the whole circuit, that is through the internal as well as the external circuit. The terminal voltage is the work done in flowing a positive charge through the external circuit only. Then we have a comparison of EMF and PD, potential difference. EMF is the maximum potential difference between the two electrodes of the cell when no current is drawn from the cell. Potential difference is the difference of the potential between any 2 points in a closed circuit. Second difference, EMF is independent of the resistance of the circuit. Potential difference is proportional to the resistance between the given point. The term EMF is used only for the source of EMF. Potential difference can be measured across any 2 points of the circuit. EMF is greater than the potential difference between any 2 points in a circuit. Potential difference is greater than the EMF when the cell is being charged. The terminal potential difference of the cell is equal to the work done for the flow of unit charge in the external circuit. V is equal to W external upon Q. When a voltmeter is connected across the cell terminal, it reads the potential difference V and not the EMF. That is the basic difference. When we are connecting a voltmeter across the ends of the cell, it reads out terminal voltage. Okay. The next important point that we are going to discuss is internal resistance of a cell. So when I was talking about the EMF of the cell, a cell is connected in a circuit, an external circuit which has got wires, other instruments such as voltmeter, ammeter, resistance that is connected in externally. So that is known as external circuit. Now there is a cell. Inside the cell there is an electrolyte in which the electrodes are being dipped. So the resistance offered by the electrolyte of the cell to the flow of current through it is called the internal resistance of the cell. So external circuit, it is connected with the help of a conducting wire, but inside the cell there are terminals of the cell that are dipped inside the anode and the cathode that are dipped in the electrolyte, and the current has to flow through the electrolyte. So the resistance or the position offered by the electrolyte of the cell to the flow of electric current through it is called the internal resistance of the cell. And because of the internal resistance of the cell, the energy is dissipated in the form of heat inside the cell itself. The internal resistance depends upon the following factor. It is directly proportional to the separation between the two plates. That is, larger the separation between the electrodes of the cell, more the length of the electrolyte through which the current has to flow, and consequently a higher value of internal resistance. That is, the greater the distance between the two plates, more is the internal resistance. The second point, it is Greater the conductivity of the electrolyte, lesser is the internal resistance of the cell. That is, it is dependent upon the nature of the electrolyte. Okay, it is dependent upon the nature of the electrolyte. More the conductivity of the electrolyte, lesser is the resistance offered by the electrolyte. It is also dependent upon the concentration and temperature of the electrolyte, and increases with the increase in concentration but decreases with the increase in temperature. Next point, it is inversely proportional to the area of the plates dipped in the electrolyte. The internal resistance of cell is inversely proportional to the common area of the electrolyte dipped in the electrolyte. Okay, and lastly, the internal resistance of the cell depends upon the nature of the electrodes. What kind of electrodes are we using in the cell? Okay, so it also depends upon the nature of the electrodes. Now we are going to find out the relation between EMF. E, capital E represents EMF of the cell. V, that represents the terminal voltage, and small r, that is the internal resistance of the cell. So we have a circuit diagram in which a cell is being connected to a resistance, voltmeter, and internal resistance R. So you can see in a circuit diagram there is a resistance R, capital R, then a cell whose EMF is E, and its internal resistance is represented by small r. Okay, so this is connected. The current can be measured by putting an ammeter in the circuit, and the potential difference across the resistance can also be measured by putting a voltmeter in parallel to the connection. Okay, so we know that the EMF of the cell should be equal to the terminal voltage and the internal resistance of the cell. E should be equal to V plus V. That is, EMF of the cell should be equal to the terminal voltage and the internal resistance of the cell. We know that terminal voltage, the voltage across the resistance V, if the I current is flowing in the circuit, then the potential difference across the resistance will be given by V equal to IR. So I into capital R gives you the terminal voltage or the potential difference across the resistance R, and the potential difference across the internal resistance small r is given by the formula I into small r. So we substitute these values. E equal to I into capital R external resistance plus I into small r internal resistance. Then on solving we get the equation I is equal to E upon R plus R. That is, the current flowing in the circuit will be given by the formula EMF upon total resistance in the circuit. Now what is total resistance in the circuit? The total resistance is the external resistance plus the internal resistance. So I is equal to E upon R plus R. Now here are certain points you should remember. The terminal potential difference V of the cell is not the characteristic property of the cell, but depends upon the value of the current I. It may be less than, equal to, or greater than the EMF of the cell depending upon the value of factor I. Dot. Okay. So, second point, when no current is drawn from the cell is in the open circuit. The value of current is 0, R equal to 0. So, from the equation we get V equal to E. That is, if when there is no current drawn from the circuit, then in that case the EMF and the terminal voltage are same. Third point, in the case when the internal resistance of the cell is negligibly small, I dot R may be taken 0, and in that case V is equal to E. That is, if the cell has got negligible internal resistance, then potential drop or voltage drop, that is represented by small v, will be equal to 0, because I dot R is equal to 0, since R is 0. In that case also, we can say that the terminal voltage is same as the EMF of the cell. Next, when current is taken from the cell, the term I dot R is greater than 0, and in that case terminal voltage is always less than the EMF of the cell. As the value of I increases, V will decrease. Okay, so more the current taken, the value of voltage drop across the resistance will be more. As a result, we have an equation E equal to V plus V. So V will increase and then the value of terminal voltage will decrease. So more the current drawn from the cell having internal resistance R, in that case the terminal voltage will decrease. Next point, when the current is taken from the cell, the direction of the current inside the cell is from negative electrode to the positive electrode. While in the external circuit, the current flows from positive electrode to the negative electrode. So, we have internal resistance of cell in terms of E, V and R. E equal to V plus V, that is terminal voltage plus voltage drop. We substitute the values of voltage drop, small v, that is equal to E equal to V plus IR. IR is equal to E minus V. We divide the equation by IR, that is V. So what do we get? IR upon IR equal to E minus V upon V. We get a relation R is equal to E upon V minus 1 into R. That is a relationship between the resistance, EMF, voltage and external resistance. A very important relationship. This formula R is equal to E upon V minus 1 in whole bracket R is a very important relation, because it gives out a relation between the terminal voltage, EMF of the cell, internal resistance, external resistance. There is no current involved in this formula. Okay. Then we have another important points. When the cell is charged, we send a current in the cell by some other electric source. Then the direction of current inside the cell will be from the positive plate to the negative plate. In this case, the potential difference V between the plates of cell will be greater than the EMF of the cell. So this you should remember, that the terminal voltage is always greater than the EMF of the cell when the cell is getting charged. So in that case, the equation will turn out to be V is equal to E plus IR. When the cell is getting discharged, the terminal voltage is less than the EMF of the cell. But opposite is true in the case of charging of the cell. In the charging of the cell, terminal voltage is greater than the EMF of the cell. Then we have the equation E minus V is equal to small v, that is potential. Now, as stated earlier, V can be equal to E only in three conditions: when the cell is in open circuit, internal resistance of the cell is negligible, or external resistance R is infinitely large. Next we have determination of internal resistance of cell by voltmeter method. This is a simple circuit. We have taken a resistance box and connected a cell. Across the internal resistance, across the cell we have connected a voltmeter. The key is in open circuit. No current is being drawn in the circuit. At this moment, whatever is the potential difference, that is the EMF of the cell. Now we close the key. The current is drawn. The current is drawn. We measure the potential difference across the ends of the cell. Note down the value in the voltmeter. We get the value of terminal voltage. Now, from the formula E equal to V plus V or E equal to V plus IR, I into small r, we can find out the internal resistance of the circuit. We have combinations of cell. A cell is a source of electric current. We cannot take a strong current from a single cell. Usually, to get strong current, two or more cells are to be combined. The combination of cells is called battery. Cells can be combined in three ways. One, in series combination. Second, in parallel combination. Third, in mixed grouping. Okay. So there are three types of combinations: series, parallel and mixed. So first one is a series combination. Cells in series combinations. The cells are connected in series when they are placed end to end so that the same quantity of electricity must flow through each cell. In this combination, the negative pole of the first cell is connected to the positive pole of the second cell. The negative pole of the second cell to the positive pole of the third. The negative pole of the third to the positive pole of the fourth, and so on. This is how the cells are connected in a series combination. So if there are n number of cells, they are poled positive, negative, negative to positive other, they are in series combination. Now there are certain points to be noted here. The EMF of the battery is the sum of the individual EMF. That is, if the EMF of a single cell is capital E and there are n number of cells that are connected in series, then the total EMF of the cell will be n into EMF of a single cell, that is E. So EMF of the whole cell will be equal to NE. The current in each cell is the same and is identical with the current in the entire arrangement. That is, the current flowing in the whole circuit will be the same, that is I. Now, since all these cells are connected in series, and each cell has got an internal resistance small r. So these internal resistances are also connected in series. So we find out the equivalent resistance of the internal resistance that are connected in series, that is equal to n into small r. Since there were n cells and r is the internal resistance of a single cell, so r plus r up to n will give you n into small r, that is the internal resistance of the whole combination. Then the total resistance of the circuit. There was an external resistance capital R that was connected to the circuit. So the total resistance of the circuit will become now NR plus capital R, that is the load. Now we know that from Ohm's law V is equal to IR, so I is equal to V upon R. So here I is equal to total EMF upon total resistance, I equal to NE upon NR plus R. Okay, so current will be given by the expression I is equal to NE upon NR plus capital R. Now there are two conditions that will be arising. NR, that is total internal resistance, is very small than the external resistance. Then in that case we can ignore NR. So if we ignore NR, then current value I will become NE upon R. E upon R is the current given by a single cell. So NE upon R will be equal to N times I. That is, if the internal resistance of the cell is very small, in that case if we add up n number of cells in series combination, then the total current will become n times the current given by a single cell. Is it clear? So what do we conclude? When internal resistance is negligible in comparison to the external resistance, then the cells are connected in series to get maximum current. Now the second condition could be the internal resistance is very large as compared to the external resistance, and R is very large compared to external resistance R. Then we'll ignore capital R. Now what we will get? We'll get I is equal to NE upon NR, and N cancel. So I is equal to E upon R, that is the current will be equal to single cell. So if the internal resistance is very large, in that situation the combination of the cells in series will be of no use, because the current obtained will be equivalent to the single cell. Next we have cell in parallel combination. Cells are said to be connected in parallel when they are joined positive to positive and negative to negative, such that current is divided between the cells. So all the positive terminals of the cells are connected to one end and all the negative terminals are connected to one end. And between these positive and negative terminals we connect the load or resistance, external resistance R. Now certain things are to be noted down here. When are we going to use cells in parallel combination? We have cells that are connected in parallel combination. Each cell has got EMF E and internal resistance R. The EMF of the battery is same as that of the single cell. The EMF of the whole combination is same as of that of single cell E. The current in the external circuit is divided equally among the cells. The current I is flowing through the external circuit and it gets divided equally in all the cells. Now each cell has got certain amount of internal resistance also. So the internal resistance are now combined in parallel. So the equivalent resistance will be decreased. The equivalent resistance will be equal to the reciprocal of the total internal resistance is the sum of the reciprocal of the individual internal resistance. That is 1 upon equivalent resistance will be equal to 1 upon R plus 1 upon R up to n upon R if there are n number of turns. So total resistance will be equal to R upon n. So what do we get? Total EMF of the cell E, total internal resistance of the cell R upon n, and capital R is the resistance that has been connected in the external circuit. So the total resistance of the circuit is R upon n plus capital R. This is the total resistance of the circuit. Next we have the current. Now the current is equal to EMF upon total resistance. So I equal to NE upon NR plus R. Now here also there will be two conditions. If R is, that is, the internal resistance is very small than the external resistance, in that case we will ignore the internal resistance. Then I will become equal to NE upon NR, N into external resistance. N से N cancel हुआ, then the current will be equal to E upon R, and E upon R is the current given by the single cell. So if the internal resistance of the cell is very small, then there is no advantage of connecting the cells in parallel, because in that condition the cell combinations in parallel will give you only the current equivalent to single cell. Then there is a second condition. If the internal resistance is very large as compared to external resistance, then in that situation we will ignore N into capital R, that is N into external resistance, and what we will get? We will get I is equal to N E upon R. This current is nearly n times the current given by a single cell. Hence, when the internal resistance of the cell is much larger than the external resistance, then the cell should be connected in parallel. Okay, so if the internal resistance of the cell is much larger than the external resistance, then the cell should be connected in parallel combination.